Welcome back, everybody. I'm so happy you're here. This is CHEM300, and we're continuing Chapter 6 today with counting atoms by the gram. So our goals in this section are to use Avogadro's number to convert to moles, and vice versa, given the number of particles of an element. And then we're also going to be using the molar mass to convert to grams, and vice versa from the number of moles of an element. So we're going to be using Avogadro's number as well as the molar mass in this section over and over again to do some conversions. So I like chemistry memes. I think they're funny because I'm a chemist, but this is one of my favorites. Hey, I just met you and this is crazy, but here's my number, 6.022 times 10 to the 23rd, so call me maybe. Avogadro is just ahead of his time, right? Okay, so a little review from last time. Avogadro's number is simply the number of particles of a substance in 1 mole of that substance. So 1 mole of, say, atoms or a molecule is 6.022 times 10 to the 23rd pieces of that molecule, or numbers of that atom. And we call this Avogadro's number. Avogadro's number relates the moles of substance, the moles, the counting unit in chemistry, to the number of particles of that substance. And so because it shows the relationship between 2 different units, moles and particles, we can use it as a conversion factor anytime we want to go from, say, number of atoms to moles of atoms, or from moles of atoms to number of atoms. And so to use Avogadro's number as a conversion factor, just like any other conversion factor when we did dimensional analysis, you can write the conversion factor with an equal sign between it. And then every conversion factor could be written as 2 different ratios. Here we have the first one, 6.022 times 10 to the 23rd particles, whatever you're counting, atoms, molecules, jelly beans, per 1 mole of that substance. Or for every 1 mole of substance, there's 6.022 times 10 to the 23rd particles of that substance. So Avogadro's number is going to be used as a conversion factor to convert between the number of particles, something you're counting like number of atoms or number of molecules, to moles of substance. And you can go back and forth. You just have to pick what ratio you're going to use in order to go from moles of substance to particles, or from particles to moles. It's the same conversion factor. You just pick a different ratio depending on what direction you're taking the problem. So let's do some examples to illustrate that. Let's convert from moles to atoms using Avogadro's number. So let's calculate the number of atoms of carbon in 5 moles of carbon. So we're given that we have 5.0 moles of carbon, and we want to find number of carbon atoms. So anytime you're going between number of whatever substance you're looking at, number of atoms, number of ions, number of molecules, and moles of that substance, you're going to use Avogadro's number. So use NA, Avogadro's number. It's the way we convert between counting objects and the chemist unit of moles. So we're given moles of carbon, so we're going to start there. Moles of C. We're going to convert to number of carbon atoms. And we're going to use Avogadro's number to do that conversion. So Avogadro's number says that there's 6.022 times 10 to the 23rd carbon atoms in 1 mole of carbon. So we're going to set this conversion factor up as a ratio when we set up our dimensional analysis problem so that we can cancel out the unit we want to get rid of. We're going to be getting rid of the units of moles of carbon, and we're left with the unit we want to solve for, and we're finding number of carbon atoms. So let's set this up down below. So we're starting with 5 moles of carbon. And now we need to plug in our Avogadro's number as a conversion factor. So we want to get rid of moles of carbon. So we're going to put 1 mole of carbon on the bottom of that conversion factor. And we want to end up with number of carbon atoms. So we're going to put 6.022 times 10 to the 23rd carbon atoms on top. And now if we check our units, moles of carbon and moles of carbon cancels out, and we're left solving for the number of carbon atoms, which is what we wanted. So you can give yourself a smiley face there, meaning you likely set it up correctly if your units end up canceling out correctly. So now it's time to plug it into your calculator. So I'm going to take 5 times 6.022 times 10 to the 23rd. And I get 3.011 times 10 to the 24 carbon atoms. So our final step is to check our sig figs and then just conceptually think about if this answer actually makes sense. So let's start with our sig figs first. We had 5 moles of carbon with 2 sig figs. Avogadro's number has 4 sig figs. Per 1 mole of carbon, that per 1 mole, that's infinite. So we've got 2 sig figs and 4 sig figs, so our final answer is going to be limited to 2. So we're going to round it right there. So we end up getting 3.0 times 10 to the 24 carbon atoms as our final answer. Now check to make sure this makes sense. We have 5 moles of carbon, and we ended up with a whole boatload of carbon atoms. And if you think about it, this makes sense because carbon atoms are very, 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 very small. And we know that in 1 mole of substance, we have 6.022 times 10 to the 23rd pieces of that substance, in this case, carbon atoms. So we expect a lot of carbon atoms to be contained in 5 moles of carbon. We got a very, very large number, so that makes sense. If you had accidentally flipped this ratio, put it the wrong way, put 6.022 on the bottom, you would have gotten a negative exponent, a very, 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 very small number, which wouldn't make sense that we have a small number of atoms in 5 moles of a substance. Okay, let's do another example. So a group of helium balloons contains 3.44 times 10 to the 24th helium atoms. How many moles of helium is in the group of balloons? So we're given that we have 3.44 times 10 to the 24th helium atoms. And we want to find moles of helium. And so this is a problem where we need to convert from number of atoms to moles of substance. Number of atoms to moles of helium. And anytime you're going between the chemist's counting unit of moles and the number of particles, whether that be atoms, ions, molecules, whatever you're counting, you're going to use Avogadro's number. And in this case, because we're starting with number of atoms and we want to end up with moles, we're going to set it up where 1 mole of helium per 6.022 times 10 to the 23rd helium atoms. So let's solve this out. So let's start with our given value, 3.44 times 10 to the 24th helium atoms times our conversion factor. And again, we want number of atoms to cancel out so that we can convert that to moles of helium. So in Avogadro's number, we want the mole part, 1 mole of helium, to be on top of our conversion factor, our ratio, and the 6.022, the number of atoms in 1 mole, to be on the bottom. And now if we check our units, helium atoms and helium atoms cancel out, and we're left with just moles of helium, which is what we wanted to find. So now it's a matter of plugging it into your calculator. Do this one along with me at home. It's a way to check that you're plugging things into your calculator correctly when plugging in Avogadro's number. And a big tip that I will give you is when Avogadro's number is in the denominator, when you're dividing by it, put all of Avogadro's number inside parentheses in your calculator. It's going to help your calculator keep this together in scientific notation. Some calculators will take your given value, divide by 6.022, and then multiply the answer by 10 to the 23rd. You need to divide by this whole number in scientific notation. So the best way to make sure your calculator does that for you is to put it in parentheses. So 3.44 times 10 to the 24th divided by, and now in parentheses, 6.022 times 10 to the 23rd. And I get 5.71238, and it just keeps going and going, moles of helium. So last couple things we need to do. We need to check our sig figs, and then we want to ask if it makes sense. So let's do sig figs first. We've got 3 sig figs in our starting value. We have 4 sig figs in Avogadro's number. So we're going to round to 3 sig figs. So 5.71 moles of helium in this group of balloons. And now, does this make sense? We started out with more than 1 mole of helium atoms, 3.44 times 10 to the 24th. We know that 1 mole of atoms is times 10 to the 23rd. So we started out with more than 1 mole of helium atoms. So we expect to get a number that's greater than 1 here. And we got 5.71. So it makes sense. It's a way to check that you didn't accidentally mess up this ratio and flip it the wrong way. Okay, so this brings us again back to talking about molar mass. Molar mass is the mass in grams of 1 mole of substance. It's numerically equivalent to the formula mass, but simply the units are different. It's in now units of grams per mole. Just like Avogadro's number can be used as a conversion factor, molar mass can also be used as a conversion factor. It relates the mass in grams of 1 mole of substance. So for whatever substance you're working with, it relates the grams of that substance in 1 mole of that substance. And so just like we did with Avogadro's number, we can also use molar mass as a conversion factor. We set up the top one with the equal sign as our main conversion factor. Whatever grams of substance equals 1 mole. And again, you find X by calculating the formula mass. You can then set that up as 2 different ratios. You can say X grams of substance per 1 mole, or for every 1 mole of substance, there's X grams. So you'll use the molar mass, which is typically written as grams per mole, as a conversion factor anytime you want to go between the moles of substance and the grams of substance. And this is done all the time in the chemistry lab because we weigh things in the lab and then we convert to moles so we can count. And then we know once we have moles of substance, we could use Avogadro's number to go to number of atoms or number of molecules. So anytime we want to go from the mass of something, which is what we work with in the real world, to counting things, so we can theoretically and use chemical calculations to determine kind of what we need to do for a reaction. Anytime you're going from weighing something to counting objects, you're going to have to go through moles. And so anytime you want to go from mass to moles or moles to mass, you're going to be using the molar mass to do that conversion. So let's do some examples to illustrate this. Let's use molar mass as a conversion factor. So let's calculate the moles of carbon in a 0.58 gram pure diamond. So we're given that we have 0.58 grams of carbon. We're assuming our pure diamond is all carbon. And we want to find moles of C. And so this is a conversion where we're going to be going from grams of carbon to moles of carbon. And anytime you go from grams to moles, or if we took it from moles back to grams, we're going to be using the molar mass to do that conversion. So we're going to use molar mass. And so carbon's an element, so we can determine its molar mass by looking at the periodic table. Molar mass of carbon, 12.01 AMUs is the atomic mass of carbon from the periodic table. We simply change the units, 12.01 grams per 1 mole. So this is our molar mass of carbon. We're going to use that to take our grams of carbon and convert that to moles. So as we solve this out, we're going to start with our given 0.58 grams of carbon times our molar mass as a conversion factor. And in this case, we want to get rid of grams of carbon and to figure out how many moles of carbon we have. So when we set up this conversion factor, the molar mass, we want the grams part to be in our denominator, so it cancels out with our starting grams of carbon. So 12.01 grams of carbon for every 1 mole of carbon. Now, if we check our units, grams of carbon and grams of carbon cancel out, and we're just left with moles, which is what we wanted to find, so you can give yourself that nice smiley face. Okay, so let's plug this in. 0.58 divided by 12.01. I get 0.048293 moles of carbon. And then you're not quite done. You need to check sig figs. So we started out with 2 sig figs in our mass. Our molar mass has 4 sig figs. So this is all multiplication or division in this problem. So we're going to be limited to 2 sig figs in our final answer. Look to the right to see if we need to round it, and we don't. So you end up getting 0.048 moles of carbon as your final rounded answer with the correct number of sig figs. And you want to kind of check, does this make sense? Well, we started out with about 0.5 gram of carbon, and we know that there's 12 grams in 1 mole of carbon. So we expect there to be not very many moles in 0.5 gram because we know it's significantly less than 1 mole. 1 mole of carbon would weigh exactly 12.01 grams. So we expect to get a small number, and we did. Okay, let's do some more of these. So this is a popular question. You'll see it on a lot of chemistry exams. It says, what is the mass in grams of 1 atom of copper? So in this one, I think the trickiest spot when I first looked at this one is identifying my given. And my given in this question is 1 atom of carbon. Given 1 atom, of copper. So if we're starting with 1 atom of copper and we want to go to mass, we can't go straight from atoms to mass. We've got to first go through moles. So if we develop a plan, we're going to start with grams. We're going to start with 1 atom of copper. And we eventually want to get to grams of copper. And there's no direct way to go from atoms to grams. So we have to go through moles, the chemistry counting unit, to get there. Just like with the hardware store when you weighed nails, you had to convert the mass to dozens of nails, and then you had to convert that there's 12 nails in a dozen. So we can't go straight from number of atoms to grams. We need to go through moles on our way there. So to convert from atoms to moles, that's an Avogadro's number conversion. And to convert from moles to grams, that's a molar mass conversion. So if we set this up, plug in what we're given, we start with 1 atom of copper. We're going to use Avogadro's number to convert atoms to moles. So for every 6.022 times 10 to the 23rd atoms, there's 1 mole of copper. And then we need to convert from moles of copper to grams of copper using the molar mass. So copper is an element, so we can check its atomic mass on the periodic table. It's 63.55 AMUs, which means that its molar mass is 63.55 grams per mole. So 1 mole of copper weighs 63.55 grams. That's the molar mass. And again, I got that from the periodic table. I looked up the atomic mass of copper and then converted it to units of grams per mole. So 63.55 grams of copper equals 1 mole of copper. And I want my moles of copper to cancel out. So I knew which way to set up this ratio so that moles of copper would cancel out and I'd be left with just grams of copper. So let's check our units one last time before we plug it in. Atoms and atoms of copper cancel out. Moles and moles of copper cancel out, and we're just left with grams. And that's what it asks us to find. Find the mass in grams. Okay, so now I'm ready to plug it in. And I get an answer of 1.0552 times 10 to the negative 22 grams. but we need to check our sig figs. So 1 atom of copper, this one can be a little tricky with sig figs. When you count atoms, is that an exact number or an inexact number? And think about this all the way back to chapter 2 when we talked about exact and inexact numbers. Something you can count, like atoms, those are going to be exact numbers, right? You can't have half of an atom or a fraction or a portion of an atom. We know exactly that we have 1 copper atom. So the sig figs on that are going to be infinite. Then we have 4 sig figs on Avogadro's number. And we have 4 sig figs in our molar mass of copper. So in this question, we're going to end up with 4 sig figs in our final answer. So 1.055, when we cut that off with 4 sig figs, we can get rid of the 2, times 10 to the negative 22 grams of copper. That's how much 1 copper atom weighs. Okay, let's do number 2. So how many hydrogen molecules, H2, are in a 2.55 liter balloon? The density of hydrogen in the balloon is 8.99 times 10 to the negative 5th grams per milliliter. And hydrogen is a diatomic element, so we're going to be using H2 as its formula. So this is going to be a big problem. I'm going to copy and paste this one into a whiteboard so we can work on it there together. So I don't run out of space again. A perpetual problem, it seems. Okay, so let's open up a whiteboard and we'll do this one on the whiteboard. Okay. There we go. So how many hydrogen molecules are in a 2.55 liter balloon? We're given the density of hydrogen, and we're reminded that it's a diatomic element. So let's map out what we're given and what we need to find. So we're given that we have a 2.55 liter balloon, and that the density of hydrogen equals 8.99 times 10 to the negative 5th grams per milliliter. And we want to find number of H2 molecules. So let's come up with a plan. We got to start with our given 2.55 liter balloon. Density, as we learned in chapter 2, is a conversion factor. It's a way to relate volume and mass. So early in this problem, we're going to be taking our volume of the balloons, of the hydrogen gas inside the balloons, and converting it to grams of hydrogen gas. So let's start out with our volume. We're going to have liters. And one of the first things I want to do is I want to convert that to milliliters, because my density is in units of grams per milliliters, and I'm going to be using my density to convert milliliters to grams, because density relates milliliters and grams. So if I can take my original hydrogen volume and convert it to milliliters, then using the density, I could figure out how many grams of hydrogen I have in this sample. And once we know how many grams of hydrogen we have, this is going to be a molar mass Avogadro's number type of problem like we've been doing in this chapter. So we know anytime we want to go to grams to moles of a substance, we use molar mass. And anytime we want to go to moles to number of atoms or molecules in this point, number H2 molecules, we're going to use Avogadro's number. So the last conversion factor we're going to need is from the prefix table. There's 1,000 milliliters in 1 liter. We're given the density, 8.99 times 10 to the negative 5th grams per milliliter. We can calculate the molar mass of hydrogen. H2 is 2.02 grams per mole. I looked up the atomic mass for hydrogen, which is 1.01. multiplied it by 2 because there's 2 atoms of hydrogen in hydrogen gas. Got 2.02 AMUs and then converted that to grams per mole as the molar mass. And we know Avogadro's number says that there's 6.022 times 10 to the 23rd H2 molecules for every 1 mole of H2. Okay, so let's solve this out. Plug in some actual numbers and see what we get for a final answer. So we're going to start with our 2.55 liters of hydrogen gas. We need to convert that to milliliters. So for every 1 liter of H2, there's 1,000 milliliters. So we did this part. Now we need to use our density as a conversion factor because we want to get to mass of hydrogen, and then we can use molar mass and Avogadro's number to go from there. So our density says that there's 8.99 times 10 to the negative 5th grams of hydrogen for every milliliter. And I set up the density as a conversion factor with this specific ratio because I want to get rid of my milliliters of hydrogen and convert that to grams of hydrogen. So that's why I put the grams part on top and the milliliters part on the bottom of that conversion factor. Next, we're going to use the molar mass. We want to calculate moles of hydrogen at this step. Oh, we did that. And so we want to get it out of grams and into moles. So I'm going to put the grams part of this conversion factor on the bottom of my conversion factor in the denominator. 2.02 grams of H2 for every 1 mole of H2. Oops, we got one more. If I stopped here, I would have calculated how many moles of hydrogen are in the balloons, but it wants to know how many molecules. So we got to take it one more step. We're going to use Avogadro's number to convert from moles of hydrogen gas to number of hydrogen molecules. So 1 mole of hydrogen, according to Avogadro's number, contains 6.022 times 10 to the 23rd H2 molecules. So let's do a units check before we solve this to make sure we set it up right before we're plugging these things into our calculator. We got liters of hydrogen that cancel out, milliliters and milliliters that cancel out, grams of hydrogen and grams of hydrogen that cancel out, moles of hydrogen and moles of hydrogen that cancel out. And the only thing we're going to be left with, the only unit, is H2 molecules, which is what we wanted to solve or find up here. So you can give yourself that nice smiley face. So now we're ready to plug everything in. I always do the units check before I plug into my calculator because there's no sense in taking the time to put this in your calculator if it's not set up correctly. You're just going to waste time. So now that we know it's set up correctly, let's plug it in. Now I got a really big number, which is going to make sense because we're talking about number of hydrogen molecules. Hydrogen is a very small element. So in this big volume of hydrogen, we expect to have a lot of hydrogen molecules. So far my answer is making sense. I got 6.8342 times 10 to the 32 H2 molecules. So we have to check sig figs. You're never finished until you check those sig figs. So we've got 3 sig figs in our starting value. Our metric system conversions have infinite sig figs. We've got 3 sig figs in our density value. We have 3 sig figs in our molar mass. And we have 4 sig figs in Avogadro's number. So the fewest number of sig figs is going to be 3. So we need to round our final answer to 3 sig figs. So I get 6.83 times 10 to the 32 H2 molecules. And then you always want to put a box around your final answer so it's easy to find. And again, this makes sense. We started out with 2.5 liters of hydrogen. Hydrogen is a very, very, very small molecule. So we can imagine that there's going to be a lot of molecules of hydrogen gas contained in this 2.55 liters, and we got a very large number times 10 to the 32nd, so it makes sense. Okay, let's do a couple more. I'm going to switch back over to PowerPoint. What I want you to do is try these ones at home and include them in your notes for this chapter. So you can label these chapter 6, practice number 1 and practice number 2. So practice number 1 is how many aluminum atoms are in an aluminum can with a mass of 16.5 grams. And I'm going to help you get started on this one with the setup. So we're given the mass of aluminum, and we want to find the number of atoms. So when you set this up, your plan is going to be to go from grams eventually to number of atoms. But we can't go there straight away. We've got to go through that chemist's unit of moles first. We know to go from grams to moles, or anytime you're going from moles to grams, either direction, you're going to use molar mass. And anytime you're going from moles to number of pieces of substance, number of particles, you use Avogadro's number. So that'll give you a start on that one on how to set it up. See if you can solve it yourself. On the slides, I put the correct answer so you can check your work. Practice number 2, a pure gold ring weighs 1.7 grams. How many gold atoms are in the ring? So this one's going to be similar to number 1. You're starting with a mass of substance given, and you want to find number of gold atoms. So see if you can follow the same conceptual layout and plan from practice number 1 in number 2 to get that answer as well. And to check your work, both of those answers are listed there. Okay, give it a shot. Let me know how it goes. And when I do the notes check for this section, I'll be checking for both of these problems. So make sure you include those in your notes for chapter 6. Okay, that's the end of this section. Next time, we're going to talk about counting molecules by the gram. I'll see you then. Thanks, everybody.